Welcome back. Today we're diving deep into something absolutely fundamental for any VMC user. Choosing the right spindle, mechanical or electric. This decision really shapes the machine's whole character. Is it going to be a powerhouse, just chewing through steel, or more of a high-speed artist for, say, fine finishing work, getting it wrong?
Yeah.
Well, that's a costly mistake.
It really is. And our mission today, based on looking at the specs and real-world applications, is pretty clear. We want to guide you to the spindle type that genuinely matches your day-to-day work. So, to put it simply, if you're doing heavy cutting, need serious torque, dealing with tough materials, you're likely looking at a mechanical spindle.
Okay.
But if it's all about high speeds, super tight tolerances, getting those perfect surface finishes, then the electric spindle is probably where you need to be.
Right. So let's unpack that before
Yeah.
we get into which cuts what best.
Yeah.
What's the actual fundamental difference? Like physically, how are these things built differently?
Okay, yeah, good place to start. It really comes down to how the power gets from the motor to the tool. With a traditional mechanical spindle, you've got your motor, right? Usually sits outside the main spindle unit, maybe on top or behind. And that motor's power has to travel through a transmission, usually belts, sometimes gears, maybe both, to actually spin the spindle shaft where the tool holder sits.
Got it. So there are extra parts in between. A kind of drivetrain, basically.
Exactly. Think of it like a classic car. You've got the engine, then a gearbox, drive shaft. Power goes through several steps.
Okay, makes sense.
Now, the electric spindle, sometimes they call it a built-in spindle. It's totally different. The motor isn't separate. The key parts of the motor, the stator and rotor, they're built directly into the spindle housing itself. The rotor is effectively the spindle shaft.
So no transmission needed.
Precisely. Zero transmission components, belts, gone, gears, gone. It's a single integrated unit.
So sticking with the car analogy, that's more like a modern EV, where the motor might be right in the wheel hub. Super compact, direct drive.
That's a perfect analogy. And this zero transmission thing, it has huge consequences.
Yeah.
For one, control. Because it's direct drive, you control the speed electronically using a frequency converter. That means you can adjust the speed smoothly, steplessly, across its entire range. Incredible versatility there.
No, I see the elegance, but what about when things go wrong? That integration sounds complex. If a belt snaps on the mechanical one, you swap the belt, right? Maybe something an in-house tech can handle.
You've hit on a major trade-off.
Yeah.
Absolutely. The mechanical spindle uses more standard replaceable parts. Belts wear out, maybe a gear tooth chips. It's often repairable on-site, maybe even by your own team. Costs are relatively contained.
Right.
The electric spindle, it's a high-precision, balanced assembly. If something fails inside a motor winding, a sensor, even just the bearings needing replacement, the whole unit usually has to come out.
Oof. Shipped up to a specialist.
Typically, yes. For repair, rebalancing. It's a specialized job. That means potentially significant downtime and, higher service costs. That simplicity versus integration difference, it can really impact the lifetime cost of running that machine.
That's a huge point. Okay, so maintenance is one angle. Let's pivot now. Let's talk applications. Where does that simpler mechanical design really shine? When do you need, well, sheer power?
Right, let's talk grunt. When you need to remove a lot of material, especially tough stuff, quickly.
Yeah, hogging operations.
This is where the mechanical spindle is typically the clear winner, specifically because of torque. That transmission system, especially if it uses gears, it's all about leverage. Think of it like the low gears in a big truck. That multiplies the motor's force to generate massive twisting power, massive torque, particularly at lower speeds.
And that's exactly what you need for roughing, right? Big tools, deep cuts, fight against materials like stainless and Connell, cast iron. They push back hard.
They really do. And the mechanical spindle is happiest delivering that high torque in its lower to mid-range RPMs. Maybe 6,000 up to 10,000, 12,000 RPM, depending on the design. That's its sweet spot for power.
Okay, what about inertia? Does that play a role? All those belts and gears must add some mass.
It does, actually. That extra rotating mass from the motor, the transmission, it gives the mechanical spindle higher inertia, which sounds like a bad thing, maybe? But for heavy, interrupted cuts, it's actually good. That inertia helps keep the spindle speed stable. When the cutter hits a hard spot or exits the material, the momentum resists sudden changes in speed, helps prevent stalling, gives a more consistent cut under load.
Interesting. So stability through mass. But hang on, can't you just, program an electric spindles drive, the VFD, to pump out tons of current at low RPMs to get high torque?
That's a really sharp question. And yes, you can get high peak torque from electric spindle by pushing a lot of current. But the key word is peak, or maybe sustained. Exactly. Remember, the motor's inside the spindle housing. Generating all that torque at low speeds means high current, which means lots and lots of heat, generated right there in that compact unit. Even with liquid cooling, if you try to run it like that continuously, like you would for heavy roughing all day long, it's going to overheat. It'll hit its thermal limit.
So it has to back off.
Yeah.
Derate the power.
Either that, or you risk cooking the windings. The mechanical system, with its separate, often better cooled motor, can typically sustain that heavy, low RPM load for much longer without issue.
Okay, that's critical. So for consistent day in, day out heavy material removal, the mechanical design's robustness and thermal capacity make it the reliable, cost-effective choice.
Generally speaking, yes.
Yeah.
For that kind of workhorse application.
All right, let's flip the script completely. We've covered the brute force. Now, what about the other end? The pursuit of perfection. We're talking precision, super tight tolerances, maybe mirror finishes. What's the biggest enemy there?
Ah, yes. The enemy is vibration. And also runout. Any little shake, any deviation of the tool from its perfect rotation axis, that ruins precision and finish.
And this is where the electric spindle comes into its own.
Absolutely. Undisputed champion here. And it goes right back to that integrated zero transmission design. No belts flapping, no gears meshing. You eliminate the main sources of tiny, high-frequency vibrations that you inherently get with mechanical systems. Less vibration means a smoother cut, fewer chatter marks.
Run out. The accuracy of the tool's rotation.
Much better control there, too. Plus, think about those transmission components again. Gears have backlash, right? That tiny bit of slot between the teeth. Even a minuscule amount of backlash can introduce tiny, unpredictable errors in the tool's path. For complex 5-axis work or fine mold details, that's just not acceptable. The electric spindle design completely sidesteps that whole class of potential error.
So for finishing passes, especially on hard materials or milling really intricate shapes where the surface quality is everything, that smoothness is key.
It's fundamental. And electric spindles are built for this. They run at much higher speeds, 15,000, 24,000 RPM, even way higher sometimes. To handle that, they often use advanced components.
Like ceramic bearings. I've heard about those.
Exactly. Ceramic bearings create less friction, they're lighter, and crucially, they expand less with heat compared to steel bearings. Because managing heat, thermal stability, is vital for precision over long runs. You don't want the spindle growing as it warms up and messing up your dimensions by a few microns. Liquid cooling and components like ceramic bearings help maintain that stability.
Right, that makes sense. You mentioned inertia earlier, high inertia being good for roughing stability in mechanical spindles. Is the low inertia of an electric spindle an advantage here?
Huge advantage for agility. Low inertia means the electric spindle can speed up and slow down incredibly quickly, almost instantly.
Why is that important?
Think about high-speed tapping. The spindle needs to reverse direction like that. Or complex 3D contouring, where the tool path demands constant, rapid changes in velocity. The electric spindle's responsiveness is essential for that kind of dynamic movement. High inertia would just fight against it.
Okay, got it. Agility versus stability, in a way. Now, let's bring cost back in, but from a different angle. Cutting tools, they're not cheap. Does the spindle choice affect how long our tools last?
It definitely can, but it's a bit of a balancing act, again, depending on what you're doing. For the electric spindle, that super smooth, low vibration operation is great for tool life during finishing, especially with small diameter tools doing light cuts at high speeds. Those tiny vibrations in a mechanical system can cause microchipping on the cutting edge, leading to faster wear. The electric spindle minimizes that fatigue.
So longer life for delicate finishing tools?
Generally, yes, but flip it around. For the mechanical spindle, its strength is protecting tools during those heavy, deep cuts. Its rigidity and high torque fight against the main killers of tools in roughing. Deflection, where the tool bends under load, and really violent chatter. If you overload an electric spindle in a heavy cut, it might chatter like crazy, or the tool could deflect and just snap. The mechanical spindle stability prevents that, saving your expensive roughing tools.
So it's not that one is universally better for tool life, it's about which one protects the tool best for the specific type of cut it's designed for.
You've got it. Match the spindle strength to the operation's demands.
Okay, let's try and pull this all together then. If someone's listening, trying to decide, let's quickly recap the key differences we've hit on.
Sure. Speed. Mechanical. Lower range. Think 6K to maybe 12K RPM. Built for torque in that range. Electric. much higher speeds, 15K, 24K plus, very versatile speed control.
Vibration and accuracy.
Big difference. Mechanical. Inherently more vibration because of the belt's gears can lead to chatter. Electric. Very low vibration, excellent runout control, ideal for precision and finish.
And then there's the maintenance and complexity.
Right. Mechanical. Simpler design, generally easier and cheaper to repair, more robust perhaps. Electric. Highly integrated, complex, needs specialist repair, careful thermal management needed, potentially higher lifetime costs for service.
So when you're looking at that machine spec sheet or making that big purchase decision, it really comes back to the core message, doesn't it?
It does.
You absolutely have to match the spindle, the heart of the machine, to the work you actually do.
Yeah.
Roughing tough stuff most of the time.
Yeah.
Or chasing microns in complex parts.
And that leads right into the final thought we wanted to leave you with. Maybe the most critical question isn't just which spindle is better overall, or which has the most features. Instead, ask yourself this. What's the ratio in my shop? How much of our paid work involves heavy roughing versus high-speed, high-precision finishing? Is it 70-30, 50-50, 20-80?
Understanding that workload balance.
Exactly, because
Yeah.
knowing that ratio, knowing whether you spend most hours hogging steel or meticulously finishing aluminum, that tells you which spindle capability will make your machine productive and profitable for years to come. That ratio defines the right choice for your business. Choose that capacity wisely.